Hi everyone, this is the first video of Chapter 9, and Chapter 9 deals with stoichiometry. So Chapter 9 is going to combine what we've learned in Chapter 7 and Chapter 8 and allow us to do kind of calculations that actually have to do with what you might actually see in a lab, which is cool. So this is where we're really getting into being able to, figure out how much of something do we start with, how much of something then should we end with. Like if we actually go to work, or go to lab and do our reaction, how much should we make of our product? So this is called stoichiometry. So that's how you pronounce this. So this is stoichiometry. Not stoichiometry, but stoichiometry. So stoichiometry has to do with the law of conservation of mass. So we talked in Chapter 8 about the law of conservation of matter, which was that matter can't be created or destroyed, which is why we have to balance chemical reactions. The law of conservation of mass tells us that in an ordinary chemical reaction, matter can't be created or destroyed, which means that there's no change in mass, right? No change in mass during a reaction. So that means that the mass of the products, whatever we're ending up with, is equal to the mass of the reactants, whatever we started with. So the mass before the reaction has to equal the mass after the reaction, because we can't create or destroy matter, right? It's got to go somewhere. So whatever we start with, right, that mass, we also have to end with that mass. So here's kind of an example of this. So this is the law of conservation of mass. So tarnish, right, silver sulfide forms when silver reacts with just sulfur that's floating around in the air to form silver sulfide. So the law of conservation of mass. So here's our reaction that we've written above. So if you've already watched the second video from Chapter 8, then writing this reaction will make sense up there. If you haven't watched the second video from Chapter 8, that's okay. I know we're doing things a little bit out of order. Just know, the reason, right, that silver and sulfur are not diatomics, we talk about diatomics in that second video of Chapter 8, is that they don't show up in Hofbrinkel. Right, so Hofbrinkel tells us our diatomics, but since silver and sulfur do not show up, those elements don't show up in Hofbrinkel, which is hydrogen, oxygen, fluorine, bromine, iodine, nitrogen, and chlorine. Since silver and sulfur aren't up there, they can sit by themselves. So silver plus sulfur, and then silver sulfide. So the way that we're getting that formula is that silver is a 1 plus, sulfur is a 2 minus, right? This was an ionic compound because silver's a metal. So the 2 goes to the silver, the imaginary 1 goes to the sulfur, and that's how we're getting Ag2S. And then to balance the silvers, you can put a 2 out front over here, and our reaction is balanced. So that obeys the law of conservation of matter. So it's saying, right, by writing it this way, we are saying that 2 moles of silver are reacting with 1 mole of sulfur to produce 1 mole of silver sulfide, right? These numbers here are telling us that coefficients, right? Those are the coefficients from the balanced chemical equation, okay? And then if we think about this, if we, instead of writing moles, if we use their molar masses here, right, 2 times 107.9, 1 times 32.07, and then this would be the molar mass of silver sulfide, 247.9. If we multiply those together, then we're getting these numbers. And so our total, right, if we added these together, the silver, right, if we added these together, we would get that, because the mass of the reactants before the reaction has to equal the mass of the products after the reaction. So that's called the law of conservation of mass, that matter and mass can't be created or destroyed during the reaction. So whatever mass we have before the reaction, we also should have after the reaction. So we know lots of things from a balanced chemical equation. We can write the reaction, right? 2 silver solid plus sulfur solid gives us Ag2S solid, right? Silver sulfide. So we can write it. We can write other things, right? We can write atoms and formula units. Don't worry about the don't worry about this here. We don't talk about formula units for Chem 10. We could also talk about Avogadro's number, right? Before we had said, down here, like 2 moles of silver plus 1 mole of sulfur gives us 1 mole of silver sulfide. Again, these are the coefficients from the balanced chemical equation, the number in the front. But instead of using the word mole, right, we know that moles are 6.022 times 10 to the 23rd atoms. So we could plug that in there, right? And then the atoms, the atoms won't equal, but the atoms kind of do different things. So, yeah, I guess bad example. Don't worry about that for now. I'm more worried about this and this one, like I started before, and the mass. The mass is going to be the big thing here, right? The mass before the reaction is equal to the mass after the reaction. That is a law of conservation of mass. So when we are talking about this example, this is combustion, and we've talked about this problem a couple times now, the combustion of methane. So remember that the way that we recognize a combustion reaction is that a hydrocarbon, right, like methane here, this is a hydrocarbon. A hydrocarbon reacts with O2 to produce carbon dioxide, water, and then some energy, which we're not going to worry about. This particular problem says calculate the mass of the reactants, right? So that's the stuff over here. These guys, these are the reactants. And the mass of the products for the following reaction when 1 mole of methane reacts. So right now, because there's nothing in front of methane here, this is an imaginary 1, right? So we can go through and we can figure out what is the mass of 1 mole of this guy. And it's going to react with 2 moles of O2, produce carbon dioxide and 2 water. So when we look at this, right, here's our stuff. These are our reactants. So we have 1 mole of methane and 2 moles of O2. So the molar mass of methane is 16.04 grams and the mass of 2 moles of oxygen. So 1 mole of oxygen is 32.02. No, sorry, 32.00. So we multiply that by 2 because in this reaction there is a 2 there, and that gets us 64. So if we add these together, right, 16.04 plus 64, we get 80.04 grams of reactants. So if the law of conservation of mass is true, then the mass of the reactants will equal the mass of the products. So we can go through and do the same thing for the products. 1 mole of carbon dioxide, 2 moles of water. So this is the molar mass of carbon dioxide. This here is the molar mass of water times 2 because there's a 2 out front. Molar mass of water is 18.02. It looks like they've used more significant figures here. That's why they're getting this 3 instead of 36.04. If you actually multiply this by 2, they just used more numbers here. But when we add these together, then we are getting 80.04 grams of products, which is the same as the mass of the reactant. So the mass before the reaction will equal the mass after the reaction. So that is proving the law of conservation of mass. So thinking about that, this says use the reaction and data to answer the following question. So if we have 12.2 grams of magnesium and 8.0 grams of oxygen, then how much magnesium oxide can we make? And we are assuming that magnesium and oxygen are going to react completely. We have to figure out how much magnesium oxide is going to be produced. So again, remember, the mass of the reactants must equal the mass of the products. So we can figure out what is our total mass of our reactants. So if we add these together, then we're going to get 20.2 grams, right? So that is our total mass of the reactants. And since matter can't be created or destroyed during the reaction, if we have 20.2 grams of reactants, then we must have 20.2 grams of products because the mass before the reaction must equal the mass after the reaction. So go ahead and pause here and try problems 1 through 6 on your lecture worksheet. It has to do with this law of conservation of mass, talking about the mass before and after the reaction. So pause here and then we'll get back on. All right, on to stoichiometry. So stoichiometry relies on this law of conservation of mass, which means, mass can't be created or destroyed. The mass before the reaction must equal the mass after the reaction. So one thing that's new for stoichiometry is this mole ratio. So we talked about mole ratios kind of briefly in chapter 7. So like if we were to look at, iron 2 sulfide here, iron 3 sulfide, in 1 mole of iron 3 sulfide, then we have 2 moles of iron, and in 1 mole of iron 3 sulfide, we have 3 moles of sulfur. So those are mole ratios, but that is within the compound. Okay, so like within iron 3 sulfide, we have these mole ratios of the different elements. Now, though, we're going to look at mole ratios between reactants and products and things like that. So the mole ratio is a ratio of the moles of 2 substances in an equation. This is going to use the coefficients. Okay, so we are only really looking at the coefficients here. So when we talk about this, if we look, right, for every, I'm going to write down at the bottom, for every 1 mole of iron sulfide, since we were talking about that, it can react with 2 moles of iron here. So this is essentially the same as what I wrote before, but here I was looking within the compound at these, but now I'm looking at the coefficients. Okay, so I'm looking at the numbers in the front.
Someone is after the fat lady.
Sorry. The name of my doorbell is the Fat Lady because we like Harry Potter. So I apologize for the interruption. But yeah, so we're looking at the coefficients. So when I'm talking about these mole ratios in this chapter 9 stoichiometry chapter, we are looking at the coefficients. So here we are, mole ratio. So again, we're looking at these numbers in the front, 2, 3, and since there's nothing here, this is an imaginary 1, right? So if we're looking between iron and sulfur, for every 2 moles of iron, right, 2 moles of iron, there are 3 moles of sulfur. So we can write this as 2 moles of iron equals 3 moles of sulfur. And then we can write these conversion factors, right? Kind of like we've done the rest of the semester. We could put iron on top and sulfur on the bottom, or sulfur on the top and iron on the bottom. It's just going to depend on what we need in order to correctly set up our train track. We can do the same thing, right? We have 1 mole of iron sulfide is equal to 2 moles of iron. So we can put moles of iron on the top and moles of iron sulfide on the bottom, or vice versa, right? Again, depending on what we would need for each one of those for in our train tracks. And then we have this one at the bottom. This would be 1 mole of iron sulfide equals 3 moles of sulfur. So again, you're just going to need to look and see which one you need to use for your train tracks. So here's how it goes. So this is a typical problem. In the chemical reaction of iron and sulfur, how many moles of sulfur are needed to react with 1.42 moles of iron? Okay, so this is our balanced chemical equation. So we have iron, sulfur, making iron sulfide. So our first thing we need to do is to use our coefficients to write an equality of and mole ratios. So here, looking at this, I'm going to write this on the next page. Okay. So we have 2 irons plus 3 sulfurs makes Fe2S3 solid. Okay, so that's I'm just rewriting that. So our problem, looking back here, was how many we are starting with 1.42 moles of iron. That will go in the beginning of our train track. 1.42 moles of iron. Okay, and we're trying to find, this says how many moles of sulfur. So that's what we're trying to find. So we're starting with moles of iron and we are trying to find moles of sulfur. Okay, so we need to find a way to get from moles of iron to moles of sulfur. So if we look at these coefficients, we can see that for every 2 moles of iron, it will react with 3 moles of sulfur. So we can write 2 different conversion factors, right? 2 different mole ratios for this. So we could put our 2 moles of iron on the top and 3 moles of sulfur on the bottom. Or we can put our 3 moles of sulfur on the top and 2 moles of iron on the bottom. In looking at this, right, the problem I've written below, we're starting with moles of iron, and moles of iron needs to cancel down and to the right, so down here. So we need moles of iron on the bottom, which means that we will use this option here. So we're going to put 2 moles of iron on the top and 3 moles of sulfur, on the bottom, and then 3 moles of sulfur on the top. We will double check that moles of iron cancels moles of iron, and then we can go through and make sure that what you're ending with, right, moles of sulfur is what you are actually trying to find. And then once you've double checked and made sure all of that lines up just fine, you can multiply the numbers on the top, divide the numbers on the bottom, and you'll get your answer, 2.13 moles of sulfur. So that's how we use those mole ratios. Let's go ahead and we are going to try another one. So, propane gas, a fuel used in camp stoves, soldering torches, and specially equipped automobiles, reacts with oxygen to produce carbon dioxide, water, and energy. So again, this is a combustion reaction. Okay, a hydrocarbon is reacting with O2 to produce carbon dioxide and water. So you could write your own equation. I've written it below for you. And again, remember this triangle here? That just means that things are being heated during the reaction, right? Because it's burning. So it asks how many moles of carbon dioxide can be produced when 2.25 moles of methane reacts. Okay, so I'm going to go ahead and carry this over. So I'm going to write the problem. I'm going to write the balanced equation up at the top so that we have it on this page. C3H8. It reacts with 5O2 to produce 3 CO2 and 4 H2O. Okay, so that's the balanced equation. I just grabbed that off the last page. And our problem says, right, looking here, we are starting with 2.25 moles of propane. So that is what's going to go in the beginning of my train track. 2.25 moles of propane. And then we can look and see, what are we trying to find? How many moles of carbon dioxide? Whoops, that's what we're trying to find here. So we're trying to find moles of CO2. So we need to figure out what our mole ratio is. So if we look, right, there's nothing here. That means it's an imaginary 1. So that means that 1 mole of propane, C3H8, will react with, and we're trying to, will form, right, we're trying to find moles of carbon dioxide. So we look at there, will form 3 moles of carbon dioxide. So again, I'm just using our coefficients in this equality here. So now we can go through and write our conversion factors, those mole ratios. So we could put 1 mole of C3H8 on the top and 3 moles of CO2 on the bottom. Or we can put 3 moles of CO2 on the top and 1 mole of C3H8 on the bottom. So in looking at our problem down here, right, moles of propane has to cancel moles of propane. So we need C3H8 to be on the bottom. So that means we're going to use this second one here. So 1 mole of C3H8, and we'll put 3 moles of CO2 on the top. Double check. Moles of C3H8 cancels moles of C3H8, and we have moles of CO2 on the top, which is what we were trying to find, right? So then, once we've got everything set up, we can multiply the numbers on the top, divide by the numbers on the bottom, and we will get our answer, 6.75 moles of carbon dioxide. So this is how you do these mole ratio things. This is where we're stopping essentially for this first part. I would encourage you to do problems, lecture worksheet problems 7 through 9. Those are going to get you some practice doing this mole ratio. And again, I always recommend doing these lecture worksheet problems before the homework, right? Because you have the answers and you have it all worked out for you so that you can get some practice. It's not very many problems, so make sure you go through and do those.